Okay, hello again. This is the, I don't know, it's the fifth one now. The fifth, lesson 5. Yeah, I better write this down. Lesson 5. What I want you to do is to watch this in succession. Don't jump from lesson 5 and then go and watch something that we've done earlier. Everything, I'm kind of developing your knowledge bit by bit, you know, brick by brick. You have to have a strong foundation if you're going to understand the much tougher, juicier subjects later on. Do you understand me? So let's take it easy and let's do things bit by bit, you know. We've got nearly 2 years before you have your exams in the summer of not this year, but next year. And therefore the many topics, many topics that you will encounter and you have to master as they come along. All right. So just learn one thing at a time. Yeah. Don't put too much in front of you. Just learn one thing. But when you do, learn them well. Learn things in depth. All right then. So electronic configuration. I bet you remember at GCSE level, they said, what's the electronic configuration of sodium? Say, you know, something nice and simple we can all remember. So sodium has atomic number 11, right? So you would have written 2, 8, 1. 2 electrons in the first shell closest to the nucleus, 8 in the second, and 1 in the outer. Obviously it's group 1 element, isn't it? So 1 in the outer. Okay. Well, I mean, this is okay, but it is not detailed. You see what I mean? The electronic configuration that you have to write at this level is, well, slightly different. So let's develop that together. Let's go through it together bit by bit. You see, if you thought, let me get my other pen, I'll show you. If you thought that all electrons go around the nucleus in circular motion, well, only some of them do, not all of them. So what's going on? How do they actually go around? You see, the electrons that go around in circular motion, but they don't make a circle, they make a sphere. So their shape is spherical, is because even though they go in circular motion, they actually go in all directions. If that red thing you see there is the nucleus. So it goes round almost at the speed of light, and it gives you a circular motion, but in all directions. So actually it generates a sphere. A very almost empty sphere, isn't it? So in the first shell, let's write it like this. In the first shell, number 1, what kind of electrons do we have? We have electrons that only go in circular motion in all directions. What are they called? They are called the S. S what? S orbitals. You know, the subshells, orbitals. Names on the tin, isn't it? Orbital means it's just orbiting around the nucleus, right? How does it orbit? In a circular motion, in all directions. So S orbital is spherical. Every shell starts with S orbital, right? Each orbital has a maximum occupancy of 2 electrons. Right? So you have the first shell, like I say, all shells starts with S orbital, right? You have an S orbital that has 2 electrons in it. And then that's it. First shell is done. There are no more electrons in the... So if I draw something with a different color, actually, it just occurred to me, maybe it would be beneficial. So there's your nucleus. There's your nucleus. And there is your S orbital. There is your 1s, 2 orbital. First shell, S orbital, 2 electrons in it. Done. So what's happening in the second shell? Well, like I say, they all start with S orbital, don't they? All right then. So S orbital and S orbital, there are 8 electrons that we have to deal with. So 2 of them go in the... Where are the remaining 6 going? Are there other s orbitals? No. The other orbitals that are in the second shell are the p orbitals. And the p orbitals, they either go along the x-axis, so they are called px, or they go along the y-axis, so they are called the py, or they go along the z-axis, so they are called the pz. Now, if each of them has 2 electrons in it, there is your remaining 6, right? So it would be the second shell, px, 2 electron, second shell, py, has got 2 electrons in it, and then in the second shell we have p orbitals on the z-axis that has 2 electrons in it. Incidentally, we write it as x, y, z, but they all have the same energy level, right? So if somebody says, what are the energy levels that these guys like? You say, well, if this is the s orbital, right, the p orbitals, yeah, and there are 2 electrons in there, we write them in arrows, you know, opposite arrows, because of the way they spin against each other in orbits. And then the p orbitals, there's your x, there's your y, there's your z. And if this is the energy level, you realize that, you know, the 2 in there, 2 in there, and 2 in there have exactly the same energy value. They have slightly more energy than the s orbital, because they're a tiny bit further away from the nucleus, therefore they can play around a little bit more. They've got more energy. Remember, the closer the shells are to the nucleus, the closer they are to the nucleus, the more firmly they are held, and therefore the less energy they have, right? Sorry about the noise, because people are coming and going, whatever, it doesn't matter. So now that we've done these 10 electrons, now, so what do we have left? The second shell is done, so we have to start with the third shell, and again it starts with the s orbital, right? So s orbital and 1 electron in it, yeah? We have s electron and 1 orbital, 1 electron in that orbital. So that is your electronic configuration. Sometimes, if it is not particularly necessary, you can actually write 2p6, right? But sometimes it is necessary to write it as x, y, and z. Do you understand? Sometimes it is necessary to write it as x, y, z, and we talk about that when we talk about shapes of molecules, etc., etc. So that is the first shell. If this is a different color, okay. So the second shell, let's draw the second shell. I have to be draw with this pen very, very slower than I usually do. So that would be 2s2, right? And then you have the p orbitals. What's the matter with this thing? P orbital, px, py, and pz, right? So the entirety of everything that you see as orange is the second shell. And then the third shell, let's use another really nice color that you can see. Again, it starts with the, so that is 3s. And this one's got 1 electron in it, right? So if I change that, so that is 2s2, and this is the px, py, py, and pz. And of course, they all have 2 electrons in it, and 3s. So when you see these pictures in some books or whatever, they are actually for real. The question that you might be asking yourself is that how do they know the shapes of these things? Look, there are electrons, right? And electrons have negative charge, and charges can be, detected by machines. And if, for example, if they have been analyzing, for example, hydrogen, imagine if you and I see something like that, we would be thinking that this guy must be spherical. And then helium, exactly the same, right? So you have 1s1, then 1s2 for helium, then for lithium you have 1s2, 2s1, for beryllium is 2s2, so we're still talking about s orbitals, all you see are spheres. And then when it comes to boron, for the first time, you can actually see that the electrons are perhaps detected elsewhere. And if you subtract that spherical electrons from the rest, you end up with the shapes of, so they don't make it up. These things are actually analyzed. What kind of questions could they ask you? Well, I mean, the concept, now you understand, is quite simple, isn't it? The concept is pretty standard and quite simple. So they tend, maybe if they give you a couple of questions on this, but for maybe 1 mark each if you're lucky, then they would probably wouldn't give you an element. They would say, what is the electronic configuration of calcium, say 2+, calcium that has lost 2 electrons. You have to say, well, calcium is atomic number 20. So if it's lost 2 electrons, so there are 18 electrons left. So it is 1s2, 2s2, 2p6, 3s2, 3p6. Are we there already? Yeah, that's 10, that's 18, right? And no wonder when calcium loses the 2 electrons from the outer shell, it becomes stable. You see, 8 electrons. Do you want to lose or gain any electrons? No. All the orbitals are full, the shell is full, doesn't want to know about any reactivity at all. Remember, chemical reactivity is to do with electrons and electrons in the outer shell. They either want to lose or gain or share. And if these guys have a full shell in the outer, the full orbitals, why do they want to gain or lose electrons? If you leave them alone, they'll just sit in a mine somewhere for millions of years. Why would they react? Why should they react? They don't want to react. When the elements become very large, so for example, let me think about something. I'm looking at the periodic table, which you cannot see, but let's say somebody says, what is the electronic configuration of rubidium with atomic number 37? Now you're going to sit here and write all these 1s2, 2s2 and get it wrong. What you can do, it is called the Aufbau principle. Rubidium is exactly the same as krypton. Yeah? So rubidium is exactly the same as krypton, that you can write like that. And then rubidium is in, and then 5s1, because it is in the 5th period and it's in group 1. So it's got 1 electron in the outer shell and it's a 5th period. So its electronic configuration, you can write the electronic configuration of krypton as that. Rubidium as that. You can write it as krypton, 5s1. It's called the Aufbau principle, or the shorthand kind of version of electronic configuration. You would be correct to write the electronic configuration like that as well. But for the simple elements, for the ones with only 10 or 12 or 15 electrons, you just write it like that. The other thing I want to tell you is that the energy of the orbitals is another thing. And I'm not going to waste your time talking about it now. Look into your books, because sometimes you see, for example, they've written 1s, then 2s, 2p, then 3s, 3p, 3d. D orbitals, incidentally, they have 10 electrons. If you remember your GCSE, sometimes some shells have 18 electrons. Where did they come from? Because they've got d orbitals, and d orbitals have 10 electrons in them, so there must be 5 different d orbitals. Again, we talk about these later on when I discuss transition metals with you about 1.5 years from now. And then 4s, 4p, 4d, 4f, etc., etc. But the way you actually go through these things to write the electronic configuration is like a snake that is going through. But let's see if we can find something interesting here. So what you see here is that you fill up the 3p orbitals before you fall, obviously, after 3p, you fill 4s before you fill 3d orbital. So it means the 4th shell, s orbital, you fill them first, so it becomes 4s2, and then you start filling the d orbitals of the transition metal. So for example, scandium, which is the first element of the first row of transition elements, is 4s2, 3d1. Or titanium is 4s2, 3d2. Remember, d orbitals can have 10 electrons in them, but these guys only have 1 or 2 electrons. That's why transition elements are referred to as elements that have unfilled inner orbitals, inner d orbitals, because you know, the orbitals, the 3D orbitals is not filled, and then we already started filling up the fourth shell, which is 4s2. Again, I'm not digressing, it is related, but it is something that we'll discuss in more detail when we talk about the transition metals later on in the course, yeah, in module 5. Okay, I think that would do for the time being. All right, thank you.